So, good to see all of you. So, a few housekeeping things to begin with. So, next week will be our 10th week. That's the last week of the class. And it will be at the normal time on Wednesday. Again, I'll show up an hour earlier or thereabouts, get set up and answer questions, but the normal class will begin at 6 o'clock. Okay? Now, that's our last class. There have been 10 of these, and we've been able to do 10 of them without a break, which is difficult for me to do. I'm going to be gone for a while because I'm going to a conference in Europe and then doing a little bit of traveling with my wife in Spain and Portugal, and then back in October. So in the meantime, Rebecca is creating, I've yet to see any of them, but certificates showing that you have participated in the class and finished everything up and accomplished everything. So what I'm going to do is for next week, I'm going to pick a cruise Sunday that I'm going to be here, and we'll have a test on Sunday morning. Everybody that passes the test will give you a certificate, okay? And we'll try and make this a cruise Sunday that everybody can show up for if possible. Is there anybody that would have a problem with showing up on a Sunday morning? I haven't decided yet. Okay, we'll decide that next time. And so the test is going to be pretty straightforward. You're going to need to show up with at least one blank universal plotting sheet, a parallel rules, set of dividers, a pencil, an eraser, a nautical almanac, 249 tables, and a calculator, okay? Not going to be able to use a form, because you know how I am about forms, okay? Or a program or something of that nature. So it'll be somewhere along these lines. You'll be given the basic information from having taken a noon sight, and you'll determine the latitude. Then you'll be given an afternoon sun sight for the same day, and the time and distance between your latitude observation and the sun sight, so you'll have to advance that line of position to get a running fix, okay? So that would be the first problem. The second problem would be a combination of Polaris and a star, okay? So you'll get an actual fix from that, as well as the prediction for twilight for that particular day. So you'll be predicting twilight, you'll be predicting, and then you'll be doing the fix for the sun and the star. And then the third problem will be, which we haven't got to yet, will be a fix involving the moon and a planet, okay? Just a two-body fix. And you'll be predicting, well, you won't be predicting the time for that. You won't need to. I'll just give you the information for it, okay? So those three problems, and then everybody that gets relatively close, we've got a nice certificate for you, okay? So you should be able to do those, I'm thinking, in about an hour and a half or so. So what we'll do is we'll pick the time the test is going to start. I'll show up a half an hour early, so any of you that have any questions about any of those things, we can deal with it then. And then we'll start off, and you have about an hour and a half to finish those three things, okay? So again, it's a noon sight for latitude, it's an afternoon sight and a running fix, but combining those two. It is a combination of Polaris for latitude and a star, so it's a fix then, and a prediction for twilight. And then the third one will be a combination of the moon and a planet, okay? So we haven't done planets or the moon yet, so don't feel like you've missed something that you're going to have a problem with. But in case, that's what we'll go for, okay? And that you'll have a chance to practice those things as well between now and then. Alrighty? Yes, question?
Speaking of practicing, before you leave, can you supply us with a practice problem of each of those so that we have something to practice on and work through?
Yeah, I'll try and do that. Yeah, let me do one of those. That's a good idea. So I'll try and do that next time, and
then you can change the numbers on the test or leave them the same.
Well, it is an open book test because, of course, you're using books, but just the almanac and it's 249 tables. Anyway, yeah, I'll try and do that. So what I'll have next time is I'll have a couple of practice problems. But anyway, I'll try and give you guys for each one of those a practice problem.
The Sunday before the end of the month?
I'm not sure when it will be. No, it wouldn't be before the end of the month because I'm not going to be here till after the end of the month. So it'll be after I get back from Europe. So it will be in October, yeah. And I understand that not everybody might be able to make that Sunday, so we'll do something for everybody that can't do that, okay? Another question, yes.
Put all that in an email and send it to us.
Yeah, what I'll do is, Rebecca will probably send it out, but we'll pick the date next. I'll advise you of the date next time. It'll be following the crew muster on a crew Sunday, so probably at 9 o'clock. It'll be a half hour for me to answer questions or help out with you, and then between 9:30 and 11 is when there'll be the test. As to the date, don't know yet, but I will establish that next
This will
time.
be sometime after you get back.
After I get back, so this will be in October sometime. So what I intend to do next week is sort of, if you guys can look at your calendars, I'll go through and start picking likely Sundays, and if there's one or two or three of those Sundays that a lot of people can't come, or most people can't come, we won't go there. We'll just try and pick a Sunday that the greatest number of people can be present for. Okay? Okay, very good. So that's, I think that's all the housekeeping, actually. Okay, so what we're going to do is we're going to start with a problem here. This is what I want you guys to do. You haven't quite done this before, but this is what I want. We have a body for which we have a GHA and a declination. The GHA is 155 degrees, 53.5 minutes west. And the declination is 20 degrees, 30.9 minutes north. Okay? That's 155 degrees, 53.5 minutes west, 20 degrees, 30.9 minutes north. Okay, this is what I want. I want the azimuth to that. Simple as that. No sextant number, no basic information, nothing else. Just give me the azimuth. What's the ZN to that, for that position? Oh, our DR position is somewhere around here. You're going to have to pick an assumed latitude like you usually do, 33 works. And you're going to have to pick an assumed longitude that when subtracted from that GHA ends up with a whole number, just like you do for a sun site. Okay, so DR position somewhere around San Diego. I need to know the azimuth to that spot. Okay? Take a few minutes and find that out. With this here, we've got the GHA, 155, 53.3, declination is 20 degrees, 30.9. Okay? So we're going to have an assumed latitude for us, AL equals 33 degrees north, just like it's always been. You know, it's not always going to be this when you're out sailing around. You'll be changing your latitudes, of course. So, again, the GHA, 155 degrees, 53.3 minutes. Assumed longitude, I'm going to say it's 117 degrees. Sorry. Actually, I think it's closer to make it 116 degrees. 53.3. It winds up being closer that way. So 155 minus 116 ends up being 39 degrees for a local hour angle, doesn't it? Okay? And if the LHA is less than 180, then what's our ZN? It's 360. Well, sorry, LHA, we combine LHA of 39 with a declination of 20 and 30 minutes. And we get a ZN of about 101, but of course it's 101 for the even 20 degrees. We're over some, and given the D factor and everything else here, it's that 30.9 is going to end up dropping the Z from 101 to 100. Okay? So we got a Z of 100. Well, if LHA is less than 360, ZN is less than 180, then ZN equals 360 minus Z, and that gives us a number of 260 degrees equals the ZN. Everybody see something like that? What's that? 259. Well, 259 if you just made it 20 degrees even, but if you allow for the D factor, that sort of moves it over into.
Just an estimate?
It moves over. It's just an estimate. Just an estimate. But 259, I'd be happy with 259 too. Okay? So if you got 259, don't worry about it. Okay, so what is the purpose of this? What do we just do? Okay? This is, we've been thinking about this as the GHA of the longitude and the latitude of the sun. But what I actually gave you was the latitude and longitude for the entrance to the Ali Nui Haha Channel between Maui and Hawaii at the moment when the sun is directly overhead. Okay? So if you work this out, what this is, this or this, whichever one you use, is the course from where we're at now to that location along a great circle. So next day you've moved some, you've moved along to the west, and then you've got a different assumed latitude and longitude, and you do this again. And in a series of daily moves, you will sail a great circle route to Hawaii, okay, to the Ali Nui Haha Channel. Is this useful? Not very, because you're actually more interested in the wind than you are in actually doing it the shortest way. When you use a Mercator projection, which is what you made with your plotting sheet, or even when you use the chart we've been using, San Diego to Santa Rosa Island, those are Mercator projections. And the Mercator projection has two important attributes. One is that the lines of longitude don't converge. They're all parallel, right? Which it causes distortion at the northern and southern extremities of whatever Mercator projection you're using. Okay? But we're using Mercator projections that portray a part of the Earth so small, those distortions are not particularly significant. If you get out the chart of San Diego, Santa Rosa Island, you'll see that 1 minute of latitude at the bottom of the chart is a little bit different than one at the top, okay, because of that change. That doesn't happen on your plotting sheet, but it does happen on an actual Mercator chart. The other attribute of Mercator projection is that you can go from any point on that projection to any other point with a straight line. And it looks on the chart like the shortest distance between 2 points is that straight line. But that actually is never the shortest distance between 2 points. The shortest distance on a globe is a great circle. That is a line that completely bisects the Earth. So great circles are, all lines of longitude are a great circle. So if you're going someplace due north or due south, just sail due north or due south, you'll be sailing the shortest distance. Or if you happen to be on the equator and you're sailing due west or east, same thing. Equator is a great circle. That's the only line of latitude that's a great circle. All the other ones, all the other angles of all the places you might want to go, they're all at some oblique angle. And so the shortest distance will always be a great circle, not the straight line shown in the Mercator projection. Does it make much difference? Well, sailing from here to Hawaii, I think the difference is about 120 miles. You might shorten it by a day, okay, if you just were sailing that great circle. But you might lose a day or 2 or 3 not catching the trade winds soon enough, right? So you're actually almost always better off to do it that way. But nonetheless, that is basically how you would do a great circle course. A lot of navigational programs give you the great circle anyway. Now, before the advent of Mercator projections, back in the 16th century, most people, if they're plotting a course across an ocean, would have sailed a great circle because the way they plotted courses was they used a flexible batten and they put it over a globe and they saw where that batten cut the lines of longitude, and they made their compass course based on that. Okay. Now, obviously, with a globe, right, you got to have a giant globe to have any detail, right? So that's kind of awkward. And it is awkward to actually be bending this batten around and stuff like that. It's much easier to have a whole bunch of charts filed away in a drawer. David?
Please use the mic.
Oh, okay. Sorry about that. So I was saying, I'll just recap some of this. In the 16th century, you would have used a globe and used a flexible batten through the first half of the 16th century, and saw where the lines of longitude cut that batten to make your course. And you would be sailing a great circle course. Again, you'd be looking at maybe changing what you were doing based upon the winds and so forth. But that's how people determine courses instead of using a compass rose on a chart on a Mercator projection. Okay? So if you're flying someplace, if you're flying from San Diego to London, you'll know you go on the GPS screen that they give you, you're going this big arc, right, which passes over Greenland and everything. All right, you go, why are we going so far out of our way? That's actually the shortest distance, because that you're flying along a great circle. It does make a difference. Airplanes go fast enough and they go far enough that they are typically doing great circle routes places. We don't typically do that on the stuff that we're doing on small boats and sailing vessels.
So when you go to Europe this time, are you going to walk into the cockpit and make sure they've got their psych?
Damn straight, I'm gonna do that, that's right. I'm gonna say, you guys decide me to do that.
Come
So-
on.
Yeah, I know. So anyway, so really, I also gave you I gave it to you because you can kind of see how if you do things by a form and you get then someone asks you to do something slightly weird like this, it's difficult. It's harder to come up with it if you're not conversant with all this stuff. So I'm going to give you another odd one. Okay, if you're ready for this. This I'm going to give you today. It's tomorrow, and it's tomorrow morning. And what I want to know is, beginning at 9 o'clock local mean time, now I want to know the azimuth of the sun at 9 o'clock local mean time. Okay? And take a few minutes doing that. That's not that much different, except, now we're doing it for a specific day. And I'm not giving you the GHA or anything like that. So you're going to have to go through the normal thing and find the GHA. All right? 104. Okay, so the reciprocal of that, if we add 180 to that, is 180 is 284. Okay? So that is where the shadow should be falling if we've got our card lined up properly. So let's make up a sheet for us. Sorry, I need to use this. Okay, so first of all, we're going to put time. So we start off, let's start off with the courses we're going to do. And I'm going to go only halfway through. So we're going to go 0, 0, 0, 0, 1, 5, 0, 3, 0, 0, 4, 5, 0, 6, 0, 0, 7, 5, 0, 9, 0, 1, 0, 5, 1, 2, 0, 1, 3, 5, 1, 5, 0, 1, 6, 5, 1, 8, 0. And so it goes, you see? Okay, so let's say we're going to take a nice leisurely bit around the, and we're going to steer, we're going to start off with a reciprocal of 284. Okay? That's going to fall upon. Now, let's look at the 249 tables, and each time we drop in LHA, we're moving it 1 degree every 4 minutes, aren't we? So we're going to do from 9 to 9, for the first 4 of these, it's going to be 284. Okay, now we're going to get 1 more degree of LHA, though, after that. So our LHA is going to go at that point from 280, the LHA is going to go from, let me find it here, 303 to 304. So if you go to your HC, your 249 table, you see that the ZN then bumps up or goes down from 284 to 283, and it actually does that, it stays that through 2 drops, 2 degrees of LHA. So it takes us 8 of these. So for the next 8 of these, it's going to be, that's 284, it's going to be 283, 283.
Is that one at 45? What is that, a 284?
That's 284. I blew it. I'm sorry. Yeah. So 283. Let's see. 1, 2, 3, 4, 5. 283. 283. 283. So this is for 4. This is at 0900. That's 1, 2, 3. Let's see. There's 4 of these. 0904. 1, 2, 0905. And then, wait, no, sorry, these are 4 minutes apart. Yeah, 4 minutes, 0, 90, no. 8. And then, yeah, 0912. Okay, for us to get halfway around. And it's going to start off at 284, and it's going to go at 283. And then after 8 of those, it's going to drop down another one. Okay, and so it goes around the circle. So we'll want to be making that adjustment. And so if, for instance, right here it starts off instead of 284, the actual shadow falls at 283, we've got 1 degree of easterly variation. Okay? So that, a deviation, right? So to get back to magnetic, we have to add a degree. Okay? And let's say it stays at 1 degree east, 1 degree east, 0 degrees, 0 degrees, 0 degrees, and then it's 1 degree west, 2 degrees west, 1 degree west, 1 degree west, 0 degrees west. So that would be a typical pattern where if that's 0 and this is west, that's east, it would start off going like that, okay? As we're testing the ship's magnetic field, okay? And that's how we would swing the compass. And that's how we swing the compass on the California. That makes sense? So another useful thing for ASGUS. Okay, now I'm going to pass around this chart, which you've seen before, you just haven't seen a bigger version of it. Just pass that around. So that is a facsimile of Edmund Halley's chart of magnetic variation in the Atlantic. Why was he doing this? What he was trying to do, he was sailing around and he was doing exactly this exercise at various places and trying to determine magnetic variation at different spots in the world. And then connecting all of the values, all the numbers of equal value with lines, so that anywhere on one of those lines, it would be a line of constant value in magnetic variation, right? So why would you do that? Well, it might tell you roughly where you're at, okay? If you did the same thing and you did what we did and you found the variation, it could tell you kind of, and then you found a latitude line. You see some of those lines run north-south or they cut across latitude. It might tell you your position if you could combine the line of magnetic variation you were on with a noon site or a Polaris site or something like that, right? So that was what the hope was, the geomagnetic solution to the longitude problem. And so there's several interesting things about this. Halley was an astronomer, but he was commissioned into the Royal Navy as a captain and given command of this ship, the Paramour. So he was a captain in the Royal Navy with a captain's salary and everything that went along with it. And Dwayne, could we just keep that moving? Because we won't, otherwise some other people have a chance to look at it. Anyway, so first of all, a couple things. One, his other officers and his men didn't like that very much. That suddenly this guy came from out of nowhere and now he's in command of him and he's had not that much experience at sea before and he's giving them orders and running them around. So that set a pattern that, on a scientific research ship, you have the officers and crew, and then there's the scientists on board who are attempting to find out whatever the data is. And that has, since that time, pretty much adhered since. It got kind of muddy, a little bit muddy with Cook's voyages, because Cook was rated as one of the astronomers on his voyages, but he did have astronomers and naturalists with him that had a separate mission from him. So he was in command of the Endeavour and the Resolution, and he was the official astronomer on board, but that's because he had particular abilities that there were other astronomers there. But in most cases, one of those script ships takes off, it's got the regular captain and crew, and then it's got the scientists embarked aboard, and they're doing their own experiments and doing stuff. But the actual charge of the vessel is up to the regular officers and crew. All stemming back to the unfortunate episodes with the mutiny that Halley had, and the court-martials and things that ensued from that voyage. The other thing that's interesting is, you'll note, on that map, something that doesn't jump out at you as anything unusual, but look at those lines. Those are lines of constant value. It's an isonomic chart. The first time ever someone had done a chart that put some quality of nature, measurements of equal value, and plotted it on a map, okay? We see these all the time. If you look at any chart, you'll see contour lines for the depths. And if you like to hike or go backpacking and you look at a topo map, you'll see contour lines for the heights. And if they're stretched out, it's a nice, easy, flat walk. If they're all jammed together, you're either going up or down kind of steep. But those are lines of equal altitude. In this case, it's lines of equal variation. And so now you can see there are all kinds of charts being weather maps that show lines of equal barometric pressure or equal temperature or any other value. We use them all the time. But the very first one is that chart right there. They all stand for that. So Halley is associated mostly with comets, but he has all these other interesting things in his life that he did that are pretty cool. Okay? Any questions about that? Okay, so we are going to do one more thing here. Let me see if I can get my projector going. Let me take a break for just a second to get this going. Everybody see that okay? Okay. Move it up. Let's see if we can move it up. Or it's good for something else too. Okay. So go with that. Okay, so when we use the sun, it's the only thing in the sky usually. Sometimes the moon's there, but not all the time. So the sun, we go to all this trouble to fix the sun's position in the sky, and then we shoot it, and we get a line of position. We're somewhere on that line of position. We got a rough idea where, but we don't know exactly where. It's not a fix yet. So we do this in the morning, and then we calculate our time for local apparent noon, and we do a noon sight, and that gives us our latitude. Well, where those two cross, that's where we're at if we haven't moved any. But in the meantime, we might have taken that sight at 10 in the morning, and then noon was almost at, let's say it's almost at 1 o'clock, so that's 3 hours. If we're going 6 knots, we would have gone 18 miles in some direction. So of course we have to take that whole first line of position, and we have to advance the whole thing along the direction that we think we went, the distance we think we went, and then where that crosses the line of latitude, that's called a running fix. It's kind of a hybrid between a dead reckoning position and a fix. The latitude line was a fix. The other one had been a fix 3 hours earlier, but now we're using an estimated distance and direction that we're advancing in. And then just to confirm that we are where we think we're roughly at, then you would, in the afternoon, shoot an afternoon sight that's going to hit obliquely to that morning one, and then those first two sights, the noon sight and the morning sight, you advance both of them, okay? The distance and direction that you believe you've sailed since the noon sight for latitude. There should be 3 lines of position, and if they cross all at the same point, you feel like you're really hot stuff. If they make a big triangle, you kind of go, well, I did something wrong. But typically they make a small little triangle, maybe a mile on a side, and you're somewhere in the middle there. And that's again a typical daytime thing. It's a running fix. What in effect you've done is you've had to be patient and wait till the sun moved to a different spot in the sky, almost like it was a different object. So you could shoot that and then wait for it to move again to a different spot in the sky. So it's a time-consuming process, but it doesn't require, other than the noon sight, that you be at the exact spot at the right time to catch it. So stars don't have that disadvantage. They have certain other disadvantages. One is you can't use them throughout the night when you can't see the horizon, because you need to know their altitude above the horizon, so it's all dark, you can't see it. So you've got to actually be up shooting stars at twilight, okay? And so that's one disadvantage. You got to be up during twilight. You got to predict it ahead of time so you don't miss it. But if you don't, you're up there. The advantage is that you can go, there's usually several things up in the sky, several stars, and so the key is find out what they are, which ones they are, and then shoot them, and then be able to use the tables that we've already done in the Nautical Almanac and then the 249 tables to reduce those numbers down to a line of position, just like we did for the sun. Only now, because it's likely that you could shoot those things so close together, like within a minute or two of each other, it's not likely, unless the ship is really going fast, that you've moved any appreciable distance at all. So you can treat it as though you're at one fixed spot when you shoot those 3 stars, okay? So there's various ways of
Ray, can you, during the full moon, really bright moon, can you make fixes?
That's a really good question. So you can see the moon, and you can see kind of a horizon, right? Right where the Moon River is and everything. So it's tempting to do that. Unfortunately, The horizon created by the moon is a false horizon. It's actually a little bit closer to you than the real geometrical horizon would be. So it's what people do with that though is they will, if you get the moon and you get two other like stars and they're all 120 degrees apart, that error kind of cancels out. So if you can get a run, yeah, that's right, then you've got a much likelier chance of having an accurate position. And you can gauge how accurate it might be by the size of the triangle generated by those 3 lines of position. But yeah, it's important to note that. So the moon doesn't, the horizon you think you're looking at isn't actually the real horizon, and that's the problem with it. Okay? So I passed out a couple times ago this chart, which gives you sort of it's a guide to the various stars, that I think is really useful. And you can get, from Celestera, you can get, for not much money, a big version of that you can put on your wall if you want, and study it, or put on your ceiling, so when you're staring up at the ceiling, you know, can't get to sleep, you can look at stars and stuff like that. So that's one way of doing it. Another way of doing it is what we went through last time with the star finder, the 2104D. It's got 2 sides, one for the northern, one for the southern hemisphere, with the navigational stars on there, and then it's got a series of transparent discs, each for for a specific latitude. You pick the one closest to you, and you mount the disc, put the hole in the disc on the little nub or a hub on the white disc below, and then you rotate the transparent one until that arrow lines up with the LHA of Aries. And then each one of those stars, when it does that, it will tell you the altitude and the azimuth for one of those stars. And you just set your sextant for the altitude, and you aim it off in that direction, and bang, there's the star just floating right there. And it's already set. If you set your sextant ahead of it, it's already down near the horizon. You just finish the job of moving it down to the horizon. The nice thing about all of these navigational stars is they're not really all that close together. So that makes it easier to distinguish one from the other. Okay? So that's a really useful thing as a star finder. And again, it's you try and shoot a wheel of stars that are as much as you can make it about 120 degrees apart. All right, and you'll get a 3 position, or a 3 line fix that way, right at that spot. Okay, so 2 good ways of trying to find stars. Stars are pretty regular. They don't move around very much. You know, they're off in the infinite distance. There is a little bit of variation, which is why you see on the different pages a difference of variation caused by the Earth's motion itself, which is changing things like the declination and the sidereal hour angle a little bit. There's a couple of forces at work. One of them is called nutation, and it's a wobble that the Earth is engaging in that takes a long time to complete the cycle, but it does move. The stars do move around relative to the Earth's to the latitude, longitude of the Earth. And the other is nutation, which is the little jerky motions that happen as a moon is swinging around the Earth and influencing it with the sun. So the Earth is wobbling in a couple different ways, and that's causing the stars to move a little bit. Not much, but just a little bit. But if you go to the given page of your almanac, you'll always be able to find it there. And it's close enough that something like this is still always going to be useful for helping find a star. Now, what about planets? Planets are in their own weird category. They're not as weird as the moon, but they are in their own weird category. So you see something up there, and it might be near a star, you know, and you're not. There's some bright thing in some place where this star finder doesn't tell you there's supposed to be a star. How do you first of all tell if what you're looking at is a planet? Does anybody know that?
Doesn't flicker.
Doesn't flicker, right? Why is that? Well, it's because unlike stars, planets are actually pretty close enough that with a telescope you would see they also have a disk, right? There's an apparent, diameter. You can't see it with a naked eye. You'd need a pretty good telescope to see, for instance, that Jupiter or Saturn or Mars isn't a point of light. It's actually a little disk of light. It's so small that semi-diameter doesn't matter. You can treat it like a star for that purpose. But as that light passes through the atmosphere, okay, the light itself is meeting different layers of the Earth's atmosphere of different densities as the light passes through, and then the air is moving around. And the light as it comes through is wiggling, right? It's like going back and forth as it's passing through. So there's this kind of flickering that goes on. Well, compared to a star really is so far away that it's an infinitely small point of light. And so the amount of back and forth wiggling that goes on with the light is many times the apparent diameter of the star. So the stars apparently seeming to move around and flicker, twinkle, right? However, a planet, even though it still is a tiny little pinprick of light, that wiggling is so tiny, it doesn't represent a major portion of the planet's diameter. So so a planet appears fixed in space, it doesn't twinkle. The bottom line is stars twinkle, but planets don't. So if you're looking at something that's not twinkling, it's probably a planet. Now, how do you tell what planet that you're looking at? Well, what's helpful, actually, is this thing that's in your nautical almanac, right? It's a chart which gives you for each month what the meridian passage is for the given planets. That's when does the planet pass the Greenwich meridian? When does it get the highest in the sky?
What page is that?
What page is that? It's pretty early on. Yeah, so if you open that up, you'll see that there's this band going around the middle, okay? And then there's this sort of hatched area, gray hatched area, okay? If there's a planet that in a given month, part of the month that we're in, like if you look at the first part of September, you'll see that in that hatched area, Mercury's getting pretty close, and Saturn is well within it. That means you can't see them. They're too close to the sun. You'll never be able to see that planet because they're following the sun very closely. If they are if they are above that line and above the hatched area, you're going to be able to see it in the morning. If they're below the hatched area, you're going to be able to see it in the evening. So you can eliminate a couple planets right away, and then you can sort of gauge them for how close to the sun they are. So Venus is pretty much I'm sorry if it's in the lower part, it's in the morning. So Venus is a morning star this time of the year, and its time of meridian passage is a couple hours before the sun sets. So we'll see it in the morning before the sun rises. Mars, we will see, it's several hours before in the middle of the night. Likewise, Jupiter, kind of in the middle of the night in the evening. Okay? So based upon what month it is and the time of the month, and you can look at this and determine the meridian passage of the planet and determine, okay, I'm looking at something, it's not twinkling, it's a planet, which planet is it? Using this chart, it's pretty easy to figure out which one it is. Okay? Does that make sense to everybody?
So the upper part is morning or evening?
Actually, the upper part is evening. So if you look at, for instance, in September.
Is that Greenwich time?
Well, it's the time of it's the local mean time of meridian passage. So it's for us. So meridian passage for Jupiter in September occurs at about 10 o'clock at night. Okay? Meridian passage for Venus, right about now, occurs at about 10 in the morning. Okay, well, it's too bright to see it 10 in the morning, but we'd see it earlier than that. It's just that's when it's the highest
When you
point.
say meridian passage, that means straight over.
That means our meridian, yeah.
Yeah.
When is it? It's noon for the planet, effectively. So yeah, so that's when that planet passes. It's noon, right? Okay. So it's actually at first it doesn't look very accessible, but once you start looking at it, you realize it's really a pretty cool device for determining what planet you're looking at. Degrees. That actually, I believe, is the azimuth, if I'm not mistaken. You know, I never look at those, so I may be wrong on that. Okay, very good.
Last night, Venus was pretty much 270, right during twilight,
It was due west
pretty much.
in the evening. Okay. Well, okay.
It shows it. It shows it.
Yeah, it's
Yeah. Yeah. Okay, well, spend some time looking at that. It's a fun thing to do. There is one other, however, pretty cool thing that I want to tell you about. I'm going to pass that information out. Hang on just a second. some of you, how many of you brought your, a copy of Volume 1 with you in today? We got one person? Two people? Okay. You guys don't need a handout. I'm going to pass this stuff out though. There we go. I'm going to pass that around. Pass this from over here. So we tried to make a copy of the relevant page in Volume 1, and also something called Table 5, which is at the end of Volume 1. What's that?
It's right here.
Oh.
You guys not seen it already? You haven't seen it? I'm sorry. I'm not the one hogging it.
Okay, so I'll wait till this whole thing gets passed out. You guys have a chance to look at the page. But we are looking at page, hang on. It should say page 94 and 95. Is that what all you guys are looking at? Okay. All right, so Volume 1 is it's a pretty cool publication, and it really makes the whole process of shooting star shots much easier. Okay, I'm going to cut this for a second. Okay, so if you look at that, either on the book or the page, what you'll see for latitude 33 degrees north is that's the top of the page. Then you'll see running down the side, you'll see 4 columns, okay, and running down the sides is LHA of Aries. That's local hour angle of Aries. To the far left, it begins at 0 and it runs down to 89. Then the next column to the right starts off at 90 and goes to 179. Then go over to the next page, it begins at 180 and goes to 269. And then column number 4 is 270 to 359. So all possible local hour angles of Aries are there. Okay, so you calculate the local hour angle of Aries, and then you find out what that is, and you do that for a nautical almanac. And you see going across for each local hour angle of Aries, you'll see 6 columns. Each of those columns is a star, okay? And the names of the stars are either in uppercase or lowercase. What does that mean? Well, the ones in uppercase are first magnitude stars. They're the brightest ones. The one in lowercase are not quite as bright, but you can still see them. So that gives you a sense of the relative intensity of the light. What you'll also see is a little diamond right to the left of 3 of the stars in each one of those columns. See that? Okay. So first of all, these stars are picked. These 6 stars are picked because there's not any other navigational stars close to them. So it's not easy to confuse them with something else. Okay. In addition, the 3 stars that have the diamonds, those are there because those stars are just about 120 degrees apart, right? As close as it can get. I'm sorry?
Where are the diamonds?
Tiny little diamonds. Look at the names of the stars.
Right next to
Every page.
Right next to the name.
Next to the name of the star. See? So little tiny little diamonds. Each one of those, for an LHA, there'll be 3 stars identified, okay, for an LHA of Aries. All right? And it will tell you for any LHA of Aries, for all the stars, it will give you an HC and a ZN. Okay? Okay, now it gets even cooler than that, because if you have an LHA of Aries and you identify the 3 stars and you go ahead and you set your sextant up for the HC, that gets you close, and you aim in the direction for the ZN, which it gives you here, you see this star there, and it should be close to the horizon. You finish getting it down to the horizon, you mark it, and you take the shot, and that's a position. But what if right at the given moment of the LHA, someone says, mark, and you've got it down there, and you've got your sextant lined up, you've zoned it in, it's on the horizon, and you read off the sextant reading, okay? Remember, we're changing 1 degree of longitude every 4 minutes. Exactly 4 minutes later, you've got the sextant set up for the next star in your sequence with the proper altitude and the proper azimuth. And when that, and 4 minutes later rolls around, you say, Mark, you nailed that one. Now, if these are exactly 4 minutes apart, it means you can use the same assumed position, the same latitude, the same assumed longitude. So you can plot from just one spot, right? You don't have to treat them all separately. And then 4 minutes later, you get the third star in your sequence, okay? And you set the sextant up for that. You got 4 minutes to get ready. You aim it in the right direction, and someone's saying 30 seconds, 20 seconds, 10 seconds, mark. You get it right down there. You write down the HO, okay? And then you go ahead and you correct for the dip and the main correction for each one of those. But you've only had to plot from this one assumed position. Now, if you really want to do all your homework ahead of time, okay, well, instead of correcting the sextant after you shoot the site, you can go ahead and do it ahead of time. So for instance, let's say you're 6 feet. So it's going to be the same dip correction for each one. And so instead of subtracting it from the HO, add it to the HC. Okay, same thing. And you do that ahead of time, earlier in the day when you planned all this out. Likewise, for the main correction, that's going to be a negative number too. So instead of subtracting that from the HO, add that to the HC, right? So you alter these HCs by the dip and by the main correction, and now what you got, it should be really accurate. Then all you have to do is you've already picked the time you're going to be up there doing this because you've predicted twilight. Okay, you decide the time you're going to shoot your first star. Let's say it's 10 minutes into twilight or a certain number into twilight, and the next stars will be exactly 4 minutes after that. You've already got your assumed position plotted on the chart then, and you have already drawn the line, the ZNs out from it. And not only that, all you need now are those sextant numbers to tell you the intercept, how far towards you or away from the star you are along that zenith line. So frankly, when you get down to actually doing this wheel of stars, it takes you 8 minutes to shoot them. It will take you like a minute or 2 minutes to work the site out. Because all you got to do is compare your HO, or the HS, excuse me, to the corrected HC, and you got it. So let's just go through the exercise there. If I can find my page for that.
Ray, do you find it hard though to find the stars sometimes?
Well, sometimes, yeah, it could be there's clouds in that direction.
Or just get stabilization.
Yeah, if the boat's moving around, it's like everything else, that can make it really difficult if the boat's moving around. So that could be a problem. It could be that the horizon is cloudy, like it is around here very often at night, you know? So these can be problems, but this is about as easy as it gets for stars, really, because it does all the work for you. So for the heck of it, let's do this. Let's say we are talking about today, September 3rd, 2024, okay? And let me get another piece of plastic. So, September 3rd, 2024. Okay. So what we're going to do first of all is we are going to actually, let's see, what did I do here? I can follow what I did a couple of days ago, and that's sometimes not easy to read my handwriting. Okay. So, civil twilight for day at our latitude in GMT, civil is 18 hours. 48 minutes, and nautical is 19 hours and 18 minutes. Now, that's for the Greenwich Meridian. So to find out what it would be GMT, our time, and local mean time, we would add 49 minutes, because we're going to add, we're 7 hours and 49 minutes on, right, from an arc, but then we're going to subtract it again for the time zone. So if we want to find out when local mean time is going to pass our meridian at 49 minutes to each of those. Okay, and that ends up giving us 18 hours, 97 minutes, which we can't have, of course, and 19 hours, 67 minutes, which then turns into 19 hours, 37 minutes, and 20 hours, 07 minutes. That's local mean time. Now, let's say that this is civil twilight. That's about the earliest we're going to start seeing stars, is about 7:37. Okay? So, let's say that we're going to start our shooting local mean time at 19 hours and 40 minutes. Gives us plenty of time should something go wrong. So we're going to start at 7:40. Now, to find out, we got to get the local hour and Aries. So what we have to do is we're time zone plus 7, and that gets us to 26 hours, 40 minutes GMT, right, when we're going to start. Okay, which is the same as 2 hours, 40 minutes GMT on 9/4/2024. Okay, so in Greenwich Mean Time, it's going to be 2 hours and 40 minutes even. As usual, our assumed latitude is 33 degrees north. Okay, and so what we need to do now is find the GHA. So GHA of Aries at 2 hours and 40 minutes. Okay, if you look up for that date on September 4th, which I hope you'll find, if I'm right, 13 degrees, 21.4 minutes. Okay, that's the GHA of Aries for the day and the hour. For the minute and seconds, in this case, it's just the 40 minutes. Okay, we're going to add 10 degrees and 1.6 minutes. Okay, so that gives us 23 degrees, 43.0 minutes. Okay. Yes. Okay. That is the GHA of Aries. But we're going to subtract our assumed longitude from that. So we're going to have to add 360. And that will give us 383 degrees, 43.0 minutes. Okay? That's the same. This 23 degrees, 43.0 is the same as 383, 42.0. But that lets us subtract our assumed longitude of 117 degrees, 43.0 minutes. So 117 degrees, 43.0 minutes. And that gives us a local hour angle of Aries of 266 degrees. Okay, local hour angle there is 266. Now, go to the proper page in that you got that I just passed out, and my eyes can adjust. Go to LHA 266, which would be on page 95. Okay, and local hour angle 266 These are the stars I see: Deneb, Antares, and Alkaid. Have little diamonds by them. Okay, Deneb, Alkaid, and Antares. Okay, so if we go to 266, and we're going to shoot, let's say we're going to shoot Deneb first, we have an HC of 53 degrees 30 minutes. So let me get another sheet of paper of plastic here.
Reading these 50 minutes.
7 LHA. So that should have been 2745. The ZN is still 199. So I don't know if I did that. Did I say, oh, wait a minute, that's Sagittarius. Sagittarius and Antares, I'm sorry. Antares at 267, yeah, 27 degrees 45 minutes. Instead, 28 degrees over 2 minutes. Okay, so instead coming across, do you see where the difference is? It's that we dropped down 1 LHA. So let me just make this correction here.
So you're doing them in 4-minute increments?
Exactly 4 minutes apart. So instead of 2802, this one now becomes, was it
27:45.
2745? And the 2.4 and the 7 equals 3.1, right? 3.1. So that gives us 27 degrees 48.1 minutes. And then for Alkaid, we're going to drop down from 265. What was our? It was 265, wasn't it? No, 266. So we're going to go to 268, right? Because it's going to be 4 minutes later. So 268 for Alkaid. That gives us 42 degrees 46 minutes. So Alkaid then becomes 42 degrees 46 minutes, and then this 3.1, so 42 degrees 49.1 minutes. Okay, so we'll need that now. So our corrected HCs are respectively for Deneb 53 degrees 53.1. For Antares, 27 degrees 48.1, and for Alkaid, 42 degrees 49.1. Okay? All right. So we could have done this first thing in the morning, right? And we could even actually go to our plotting sheet. And gone to latitude 33 degrees north. And what was our assumed longitude? 117 what?
43.0.
Okay. 117 degrees, 43.0 minutes. That's assumed longitude. Okay. So we've got this spot that we're going to plot from. And the ZN for Deneb was 057. So that's in this direction. Okay. The ZN for Antares was 199, which is off that direction. And the ZN for Alkaid is 309. So let's see. So you see how these present a nice wheel. So all we need to do now is to take the site for each one of those. So at the precise, I don't know if I said, was it 7:40? At 7:40, we get up ready, get early. It's like, okay, 7 hours, 39 minutes, 30 seconds, 20 seconds, 10 seconds mark. And the first one you get is Deneb. And you write down what the HS is. And then you wait, and exactly 4 minutes later, you start your countdown 30 seconds ahead of time. 30 seconds, 20 seconds, 10 seconds mark, and you get Antares and you write that down, and then finally Alkaid exactly 4 minutes later. And then what happens? Well, let's say that you are with Deneb, you are, let's say that you're 5 minutes, your HS is 5 minutes above the HC, it's bigger, so you're towards. So you come out 5 miles, that's LOP1. Okay. Now for Antares, let's say that you are also, let's say you're 2 miles towards, you're 2 minutes higher on your HS and your corrected HC. So you come out 2 miles, and that's your LOP2. And then for Alkaid, let's say you're like 12 miles smaller. So you come out 12 miles away, and that's your position. So this is 12 miles from there to there, that's 2 miles from there to there, this is 5 miles from there to there. Okay? You can see how you could do this really fast if you wanted to and make it nice and easy. Okay, so that's why volume 1 is pretty handy to have. Okay, any questions about that? This is not going to be on the test. But just, take that sheet home and take a look at it. For doing stuff around here, the sheet that I just handed out, that's the only page you need. That's 33 degrees north. There's one last little wrinkle. The second thing we passed out was table 5, okay? If you go to the back of your volume 1 book, which most of you don't have, that's fine, you'll find something called table 5. And what does table 5 do? Well, first of all, these site reduction tables, volume 1, they're for given epochs. That is, this has a time stamp on it. So this is good through the year 2029. So this is epoch 2025. So it's the 5 years before, 5 years after. After that, get rid of this and get the next epoch out there, okay? Because all of these stars have changed a little bit. So what you would do, you go to table 5, and in table 5, you will see on that page it says 2024. And you look at 2024 and you look at your latitudes. So 40 is about the closest to us. And the LHA of Aries, and so we've just calculated LHA of Aries. What was the LHA of Aries? Does someone remind me what was that again?
266.
Okay, so 266, come down to about 270, which is pretty close. We're going in the table 2024 to 270 with north 40. Hang on. And what you will get is 0.2 minutes, and in degrees, 271 degrees. That means you move your entire fix 0.2 of a mile in the direction of 271 true. Just move the whole thing. And that's your position. And if you look at these numbers, you're talking about the biggest numbers you're going to see are like 0.4 of a mile or something. Well, I guess there's some that are like 1.3 and so forth. So what is this doing? That's to account for those little gyrations I told you about, precession and nutation. Okay? So instead of having to allow for that all the way through this book and make it a huge book, they just let you work it all out and then take that whole fix and move it that distance in that direction in accordance with what you see in table 5. Okay? And that's the end of it for that part of doing stars. So it's handy to calculate your time. Question?
Since we did all that work for 7:40 p.m. and it's almost that time, are we going to go out and use our...
Because, well, we don't I know. It'd be nice if we did, but we don't have a horizon. I don't know if we can even see them because of the... I will tell you one thing about San Diego. There's a lot of light pollution, which does make it difficult to do this. You can go to Anza Borrego, but you don't have a good horizon there. But you can also go out to sea. After you get about 30 or 40 miles out at sea, then your light pollution isn't so much that it interferes with things too much. Another question.
So when we started, we were just doing 2 lines of position, and today you just described and demonstrated 3 lines of position. Is
Yes.
there like a minimum that is 3 the minimum?
Well, three's better than 2. I don't know that 4 is that much better than 3, but 3 is pretty good. And remember, the navigational day, if you take a morning sight and then you advance it to the noon site, and then you double check in the afternoon. Likewise, you got 3 lines of position, separated by the time between and the distance that you run between. When we did stars, we did Polaris and a star, and then we did 2 stars, so just across the 2 lines of position. That third one is just a check to make sure you haven't done something really bad. So they all made a nice, intersection here that makes you feel real good. But mostly they're going to be a little triangle. And the size of the triangle, if the triangle's too big, then one of those is probably out somewhere. And in this case, doing it this way, it might be the sextant reading. It's a bit out.
So if it's a triangle, we're somewhere in that triangle.
Right, about the middle of the triangle usually is what most people figure. Okay? So again, what you do is it requires that you predict when twilight's going to be, civil and nautical. You have to allow for the fact that, it gives you those times for Greenwich, but then you got to allow for the local mean time and then allow for the time zone so that you could get the GHA of Aries. With the GHA of Aries, you can combine that in table 1, or just GHA of Aries. It'll give you the stars that you need, and it'll give you the HC and the ZN for each star. But then you can go ahead and pre-correct your sextant, the appropriate amounts. So you have very little to do, in twilight when it's getting dark. And you're only going to fix really fast. Okay? All right. Does that sound like fun? Okay. All right. We're going to take, we're not going to take much of a break because we're kind of running late. So it's not going to be a really long lecture. So this one's going to be a little bit shorter. So as we left it last time, pretty much the chronometer had just been developed, and so had the tables for lunar distance, and they both were vying with one another for what's going to take the precedence. And the chronometer, they continued to test it because it was difficult for them to get their arms around this device that was as accurate as this, particularly because the H4 was not all that accurate, or nearly as accurate when it's just sitting there in Harrison's house or at the Royal Observatory than was when you take it on a ship and jostle it around. It just was phenomenal that way. So anyway, they continued to achieve amazing amounts of accuracy, and word of it got out, and it got over to France, and so you had the horologist Ferdinand Berthoud, who visited Harrison in 1763, and he offered, he said, for a certain amount of money, will you tell me your secrets? And Harrison said, of course, no problem with that. And but how much do you have in mind? And Berthoud said, gave him a mind. He goes, no, forget it. No, it's going to be at least this much. Well, what's curious about this is that in 1763, this was something the British government had invested a lot in. They've already paid Harrison thousands of pounds. They already invested thousands of pounds in the Royal Observatory. This object was like, it had enormous potential military value, right, and value for trade and everything else. You would think it would be a state secret. Berthoud was from France. In 1763, they were in the middle of the 7 Years' War. But in the middle of the 7 Years' War, between the contest between two great empires for the ownership of North America, among other things, in the West Indies, and it was a world war. It was fought in the Indian Ocean, fought all around the world. One of the leading scientists in France just hops on a boat, sails over to England, and offers to buy the secret to one of the most important, military secrets there would have been. And nobody said, hey, you don't get to do that. And Harrison himself said, well, I'm not feeling that's a very patriotic thing to do. He's just like, that's not enough money, And nobody was ever called that. So it's just an interesting idea. In fact, in those times, scientists were given free license to go wherever they wanted to, and not be molested or bothered by the militaries of any national governments. As a matter of fact, when Captain Cook sailed on his third voyage to the one he discovered Hawaii, where he was going to go through the Northwest Passage, there was a letter written by Benjamin Franklin in Paris to George Washington saying, don't mess with this guy, okay? He's got free passage, he can go wherever he wants, he can sail in and out of any American port he wants. Just let him do what he wants to do because he's advancing the knowledge of the whole world. So in many ways, it was kind of a nicer time than what we have now in terms of what people afford one another and how much the national sentiments were constrained to just and restricted to certain areas of competition. Anyway, I forget why I have chronometer number 24 up there, except that I think that was Ferdinand Bethune's chronometer, and that he came up with. Well, in any case, Cook continued to have these things, but Harrison, they kept keeping from Harrison, they kept withholding the actual prize money. Now, Harrison, by this time, had accumulated more than 20,000 pounds in grant money from the British government to develop all of these clocks. So he had already gotten the amount of money for the prize, but he wanted the final 20,000 pounds, and he was lobbying heavily to get it. As it turns out, Harrison never did win the award never did win the longitude prize, because he was ineligible for winning it, because, as Newton said, you can't use a clock to find the longitude, you can use it to keep the longitude, but without reference to astronomy, it's just a machine that runs on its own principle, not in accordance with the laws of the universe. The award itself, Neville Maskelyne, the Astronomer Royal, was also not eligible to get it because he was a government employee. And they finally decided you can't be on the government payroll for your whole life and then find out something and say, oh, I want the award now. You got to do one thing or the other. So Harrison had kind of established the format for the private scientific enterprise, the private laboratory pursuing a technical solution funded by grant money, but still in a position to be eligible to market that invention, to market the inventions or the discoveries, as opposed to a government employee who is getting a salary and is working in a government facility that if they find something, it's really supposed to belong to the government, not to them. They don't benefit, they can't bring it to market, they can't sell the idea themselves. And there's all this gray area, of course, with intellectual property and so forth, but some of these notions were getting determined right then and there. Right, and we have been living with a precedent of that in scientific enterprise ever since. The guys that actually won the award were Leonard Euler and Tobias Mayer. They're two mathematicians and astronomers of the age that actually took, and Laplace, actually, he was the third one. They actually took the data that Flamsteed and others had assembled and that Maskelyne had assembled and used that to develop the tables for longitude. And I think they split the 20,000 pounds themselves. And they were formally awarded the longitude prize, which if you read through Dava Sobel's book, there's no mention that they even existed, you know. But they won the award. I'm sorry, Margaret? Laplace, Euler, and Tobias Mayer. Mayer and Euler were German and Laplace was French. And the three of them, you know, they three of them did it. They were given the award. So they won the longitude award, the longitude prize.
So did they do it independently, or did
They worked
collaborate?
together and collaborated, yeah. And they each reinforced each other's work and double checked it and so forth. So they were all, I think it was split up among all of them. And that kind of sets the stage for the Nobel Prize and things like that. Awards given for significant discoveries. And when it's a collaborative effort, the award or the prize is usually shared among the principals who collaborated on it. Okay, so then Harrison is still lobbying, but Harrison is really a politician. He makes friends with the King of England. They hung out together. And he makes friends with guys in Parliament like Edmund Burke. And so after the award is given to these guys, he stands up, Burke, on the floor of Parliament, says, "Where, sir, is the dignity, the sense, even the justice of the representative of a great, powerful, enlightened maritime nation, when a petition is laid before them claiming not favor but justice, claiming that reward which law would give him, and to see it refused, upon what principle? Why, a man of 83, actually Harrison was not 83 at the time, but nonetheless, is to make new watches. He's not only to make them, but to make new voyages to the Indies to try them. Good God, sir, can this be a British House of Commons? Is this conduct worthy of the munificence of this House? Of a nation that owes to her navigation, her wealth, her consequence, her fame." So it's great for somebody to have an advocate like that, you know, to try and lobby for money for you. And it's great to have the sovereign of the nation say, you know, by God, Harrison, I'll see you write it. And indeed, Harrison got the last 20,000 pounds. So they built more money, and he got it. So Harrison actually retired, not with the award, but with what he really wanted was he just became really, really rich from doing this, even though he had accumulated over his life much more than that. So in the final test, this was, or not final test, but I got this excerpt from I think it was HMS Tartar to Jamaica. As at the arrival at Jamaica, the observations for finding the time were made by equal altitudes, and the longitude them by the timepiece being within 5 seconds of time at the longitude shown by the most accurate observations of Mercury in its transit over the sun in the year 1743, and with which all the observations at London and Paris agreeing within 23 seconds amounts to a demonstration that Mr. Harrison has performed all as required by the statute of the 12th of Queen Anne to entitle him to the greatest reward mentioned in the act. Well, it wasn't, but what I wanted you to know was this was the first instance of somebody saying, yeah, this guy deserves to get the money. This guy actually solved the problem. He deserves the award. And also notice how they did it. They did it by equal altitudes of the sun, okay? They caught it on the way up, caught it on the way down. If the moon isn't out, you couldn't do that. So that was one thing you could do with a chronometer you can't do by the lunar distance method. So you've got many more chances to make an observation if you've got a chronometer that works. And of course, Cook was irritated in his first voyage when he was given Maskelyne's tables, and the voyage lasted longer than the tables had numbers for it. So he just sailed himself out of coverage for longitude. But that wouldn't have happened with a chronometer. And indeed, of the chronometers, the copies of H4 never worked. Arnold's chronometers never worked, but Larkham-Kendall's did, K1, and that's what Cook took with him, which he liked a lot. And subsequently, other explorers after this almost always had chronometers with them. George Vancouver had an Arnold chronometer. He had updated it, and he had copied Larkham-Kendall's machine, and they had drifted away from the principles used in Harrison's machine. And indeed, that's Vancouver's chart of San Diego using an Arnold chronometer to fix our position where we are right here. So it was used effectively. So was all this stuff worthwhile? Was it serious business, or was it really just affectation? Well, if you look at the 7 Years' War, and that's before chronometers or lunar distance were really available, Cook's voyages all took place after the 7 Years' War. On a tally of ships lost, British ships lost in the Royal Navy, there were 8 ships destroyed in action. There were 102 ships captured by the enemy. There were 20 ships burned by accident. 87 went down or missing with all hands, and 261 of them were wrecked. So navigation was a big deal. There were a lot of ships being wrecked in 7 years to have 261 ships go on the rocks and be destroyed. That was a pretty serious thing. But it wasn't. This tended to focus on time, because time and navigation are so interwoven. But going concurrently with this, of course, was the other clock that was significant, and that was the one that's in our bodies, the human clock, and what happens when you go to sea and you lose access to fresh food. So, we talked about Anson's voyage and how many guys died. He lost from 2,000 men that set out, he came home with about 10% of them alive. After his voyage, scurvy became an extremely important question, almost as important as longitude. And in 1747, on the cruise of a British ship of the line, HMS Salisbury, which lasted 6 weeks in the English Channel, several seamen came down with scurvy. And instead of just applying remedies willy-nilly, the surgeon at the time, James Lind, took 6 seamen. 2 of them he gave salt water to. 2 of them he gave this medication called Ward's Drop-in Pill, which was a purgative that would have helped. So drinking salt water wouldn't help. And then the third one was the common thing, because they'd only been underway a short time, is he gave them oranges. Okay, gave 2 of them oranges. The 2 that were given oranges recovered, which everyone expected they would, because people did know that citrus fruits would do that. And then Lind went on to leave the Navy, go to the University of Edinburgh, become a physician, so he's no longer just a surgeon, and then wrote a treatise on scurvy. Unfortunately, he never made quite the entire connection between citrus fruits. He just wrote that solved it. So what was it about those things, about citrus fruits, that cured scurvy? Well, it took a long time to figure that out, actually. It wasn't until the 1930s that vitamins were well understood. And people, of course, would have been unique. The problem is that fresh fruit doesn't last very long. Oranges don't last very long. But what did last fairly long were this fruit in the Mediterranean called limes. Now, when I say a lime, you're visualizing a little green fruit like this. Okay, no, the little green fruit like this grew in the Caribbean, in the West Indies, and it was called a lemon. The British started giving the yellow fruit about this big to their sailors. That was what they called a lime, what we call a lemon, and it worked really well. Now the problem is you can distill it down to a syrup if you're careful and heat it very slowly, but heat destroys vitamin C. If you render it down in copper pots or cauldrons, which is what people used a lot to cook with, copper destroys vitamin C. If you leave it out in the sunlight, that destroys vitamin C. So you had to be really careful when you did this stuff. You could really mess it up as a remedy for scurvy. But nonetheless, they began to do that and replenish ships at sea. Now, the British really developed the whole principle of underway replenishment, which was used by our Navy all the time for fuel and moving stuff. And the British Navy and the American Navy are the best at underway replenishment. But the British started that really following Anson's voyage in the 7 Years' War. And mostly this was done for ships not on far distant voyages, but on imposing blockade when they went to war against France. So up until then, up until the effective underway replenishment, and that was a program instituted by none other than George Anson, who had seen a lot of scurvy firsthand. He became an admiral, and he began to exert an enormous amount of influence over naval regulations and rules of naval life. Right? Until Anson, if you were in the Navy and you got wounded, your pay stopped until you went back to work. Right? If you were treated by a physician or a surgeon on a ship, you had to pay for that. The government wasn't going to pay for it. Right? People didn't necessarily have uniforms. Their uniform was kind of whatever they wanted it to be. There were a whole lot of things there were irregularities about naval life that are totally absent, from today, from any military service. But underway replenishment was something Anson felt really, really strongly about, and he began to implement it in all the fleets that were going to be on blockade. Well, when the 7 Years' War occurred, the French had a much more powerful army than the British did, and they, as they often did when these wars broke out, thought that they intended or hoped to be able to settle the matter by landing a large army either in England or Scotland or Ireland. And in 1759, they began to collect a huge army at a place not far from a bay near Brest called Quiberon, and just waited. Their fleet waited until the British ships blockading that all the French ships in port would get blown away by a storm. Now, that blockade went on for year after year, and it began with Anson. At some point, he handed it over to a fellow Admiral, Edward Hawke. And in normal practice, either you would have to deplete the ships to send them in to get reprovisioned and cure all the guys from scurvy, or the fleet would, in its entirety, the strength would start to wither away. The French had noticed that the ships that were on close blockade off of Brest on station weren't leaving. They were staying on station. And that meant, in their mind, half the crew's probably sick and dying. So they're probably in a weakened condition. So all they had to do was wait until the British fleet got blown away by a storm, and they put to sea with the invasion fleet. They were initially going to invade southern England, but they decided to go for Scotland. So a large French fleet put to sea from Brest. The British fleet was chased by a storm into Torbay, and there were a few ships left on station that could signal. And once the French fleet was out, the British came sailing back and caught them just off of this really rocky, dangerous place called Quiberon. Under normal circumstances, had this been years before, the French would have been facing down a fleet that was been manned by really sick people, sick and weakened people. However, Anson and then Hawke following him had been reprovisioning his ships on a regular basis. So there wasn't a single ship in Hawke's fleet that had more than 3 or 4 guys on the sick list. So they were really healthy, and they had actually been practicing their seamanship and gunnery and everything else being on blockade. So when they came sailing in, it really spooked the French. The French sailed in to this rock-bound bay filled with reefs and rocks, and basically the British fleet destroyed the French fleet at the Battle of Quiberon and ended any possibility of the French invading Britain anytime during the Seven Years' War. Up until that point, it was probably the most decisive naval battle of the modern era. But it was a big deal. Well, it ended up that the thing with underweight replenishment and solving the problem of scurvy, even if you didn't understand what caused it, that ended up being a multiplier of force evident in a case like this. So if you have a fleet of say 30 ships and you're having to send half of them away half the time for the crew to get fed fresh food, now you've got a fleet of 15 ships. But if you don't have to do that, now your fleet of 15 ships can actually look like 30 because your fleet of 30 ships can look like 60 because you don't have to send half of them away. It's basically, it's basically how the British came out on top in the 7 Years' War and kind of set the stage in a way for the American Revolution, and the French wanted to get revenge against them. But just in like fashion to what we talked about with the wrecked ships, if you looked at losses during the entire war, so during the entire 7 Years' War, which was fought largely at sea, a total of 1,522 seamen were killed in action. On the other hand, 133,708 of them died of disease while embarked on ships. To put things in perspective, Hawke's fleet that destroyed Admiral Conflans' French fleet at the Battle of Quiberon had about 20,000 men. So it was about 6 or 7 times the entire size of the largest fleet the British sent to sea that died of disease during the 7 Years' War. Okay, and this was after underweight replenishment had actually started to become a practice. So ultimately, it permutated in other ways. We kind of know how Captain Cook died. He showed up in Hawaii in 1779. He happened to arrive. He showed up at first, noted that the Hawaiian Islands were there, discovered them, fixed their position, didn't go ashore, sailed up to try and go through the Pacific entrance to the Northwest Passage. It was too late in the season. He sailed back to Hawaii, and he happened to arrive during the festival of Lono, a Hawaiian deity who arrives at a certain time of year. And there were elements of the ships, like the masts and yards, which looked a lot like the symbolism that was used in ceremony to depict the god Lono. It worked out to be really advantageous to the rulers of Hawaii, the Ali'i class, because they were the ones that had been sort of, endowed with their own special powers by the god Lono and the other gods. And so here this guy shows up from somewhere looking like it's Lono, and it looks like they summoned him. So Cook was received like a deity and treated like a deity, and anything he wanted he got, and it reinforced the authority of the Hawaiian Ali'i, or it's an Ari'i, it's Ali'i in Hawaiian, in the hierarchical class system that the Hawaiians had. So Cook was having a great time there, but he wanted to replenish his ships because he knew he was going to sail up to the Northwest Passage. They'd get trapped in the ice maybe 2 or 3 years. So he needed as much fresh food as possible. So there were really only about 60 or 70 British guys on these 2 ships, but Cook required massive amounts of food, including animals, pigs, chickens, whatever the Hawaiians had, plus breadfruit, plus pamplemousse, plus taro, anything the Hawaiians had. Cook needed massive quantities of it because he was fearful that if he got his ships in the Northwest Passage, all his guys would die of scurvy before they got to the Atlantic side. Well, the problem is the Hawaiian Islands had huge teeming populations. Those populations were already as large as what those islands could sustain. Suddenly, 100 really hungry English guys with seemingly a bottomless requirement for provision show up, and they're, it's like the in-laws have come from out of town and they just won't go away, right? And so Cook stays and stays and stays, and finally they say, well, isn't it time for Lono to go now? Because, the festival's over, and don't you have someplace to go and someplace to be? And he's getting the word that, yeah, they ought to really take off. So they took off. They only sailed about a week to the north, and they got in a gale, and the Resolution's topmast got sprung. They decided, well, let's go back to Hawaii, and we can fix that problem, and then sail off again. So Cook shows up in Hawaii at Kaliakakua Bay again, and the Hawaiians are thinking, oh my God, we finally got rid of this guy, and now he's back. He's going to eat us out of house and home. So it wasn't a very happy return. The Hawaiians began to steal things from Cook, or from the English. They stole one of his longboats, And he did what he normally did. If there was a theft problem, he would take a group of his Marines ashore and capture a local dignitary, a chief or a tribal elder, and hold him as hostage until the stolen goods were returned. It almost always worked. But in this case, by this time the Hawaiians were so sick to death of the English, they were having none of it. And on the way back to the beach, Cook's fairly small party was surrounded by hundreds of Hawaiians, and at the water's edge, they basically jumped on them all, and the British, even with their muskets, were no match for all of these big, angry Hawaiian guys. Cook was killed, and some of his other men were killed too, and that was it. Interestingly enough, I mean, Cook may have been the most famous explorer to die of scurvy, because it was fear of scurvy that actually caused this behavior in the first place, and had its own effect. In any case, both the investigation into the causes of it took the same institutional form as the search for longitude, with research institutions like Haslar Naval Hospital. So, and Lynn published his book. He continued to experiment, and that experiment that he performed on HMS Salisbury was the first clinical experiment performed in all of medical history. Okay, it was the birth of clinical medicine. And they continued to investigate scurvy by testing it on people and by using clinical trials. And then the second element of this whole process of investigation, the beginnings of epidemiology, occurred when the surgeon of the fleet, Sir Gilbert Blaine, who was surgeon for George Rodney during the American Revolution, did a quantitative survey of scurvy. How long have these guys been at sea? Where they've been Navy and so forth, over the entire fleet, and used numbers actually to validate, if not cause, then at least patterns in the outbreak of disease. That later, the same techniques were applied to cholera and to other epidemic diseases. So again, it was the attempt to determine a cause of scurvy that resulted in the first the beginnings of clinical medicine, but also the beginnings of epidemiology. So both of those things have the same sort of origin cause of scurvy and needing to solve a navigational problem, and they followed a similar pathway with institutional science, as did the search for longitude. So that ultimately, we have the National Health Service, and we have the Centers for Disease Control, and everything else, which are projections of the kinds of institutions that were beginning to emerge during this period, during the Enlightenment, in an effort to cure scurvy, because it was a navigational problem. Ultimately, this quote I thought was kind of cool. The mournful waste of the human species was more chargeable to mismanagement than anything unavoidable in the nature of a sea life, written by Nelson in 1804, recognizing that for a long, long time, all of these measures were within the ability of implementation, and people just didn't do it, not just for not wanting to be different, but because the institutional means and the systematic means for doing so had to be invented. And they were pretty much invented during this period, during the Enlightenment, both in the search for longitude and in an effort to find a cure for scurvy. There you go. End of my story for tonight. Thank you. Are there any questions by any of you?